Biot-Savart law. And then the mu sub 0 is depend on the material. When you say sub 0, means related with the free space. If you have a different material, then we're using mu. Mu is depends upon the medium. Different medium, you have a different mu. And usually is listed out in the physics handbook. Before we go on of using this, we have a lot of problem can be doing the calculation. That means the magnetic field along a circular route. This kind of problem is very common. And then we can do the circular route for infinity line and doing the magnetic field calculation. So how do we know it's right or wrong? We have another cases we are doing it is I created a section in which case is 22.78. We study together. 27A is your old section. In the box is 22.9. Besides the two gentlemen study the magnetic field created by the moving current, Ampere do the same thing. As a matter of fact, can be your lab, special project lab. So what happens is when a current goes through in the surrounding, in the plane, we like to say in a plane, we are creating magnetic field. In a magnetic field. Now, if we put the iron dust around it, then this dust will separate like this. All the dust in a certain pattern, in a circular pattern. This particular law is called Ampere's law. Ampere's law is deal with the magnetic field for the infinite long wire carry on the current. What it means is a current go through this infinity line very, very far away, so that and at one point away from the wire, in which cases the distance between that is r. So in these cases, it can say in here is a little element here is ds. ds to do it. Now the ds is not around that area. So ds is in here. So anyway, what is Ampere's law equivalent to? So when we study the electrical field and magnetic field, we always like to compare. Ampere's law is equivalent to Gauss' law. Gauss' law is for electrical field. So this is for electrical field. Our electrical field, we say the electrical flux is either go to complete integral or electrical field dot dA. So that is related with the Gauss law. Now in Ampere's law is related with a integration of the closed loop and related with the inside of the wire current. So the Ampere's law says dB is equal to integral of B dot ds. So B is in this end, ds, closed loop equal to mu sub 0 I. So if you compare with this equation, this is Ampere's law, and this is electrical field. This is Gauss' law. So one is a B dot ds, another one is a E dot dA. So one is related with area, electrical flux. This is related magnetic field in the circular loop. So this is the case. So that's one thing we know. This Biot-Savart law is related to this. dB equal to mu sub 0 divided by 4 pi I ds times R divided by R squared. So for this Ampere's law, we could do one thing. The one thing is that suppose we integrate this in a closed loop, completely closed loop. Suppose this is the R, so what is the magnetic field created by that? So if you do the complete integration of dot ds and equal to B times 2 pi R, and related with its current equal to mu sub 0 I. So the magnetic field around the current will be equal to B equal to what we call mu sub 0 divided by 2 pi R times I. So here is the function of the magnetic field for a wire carrier current I. You can do the same thing with this equation, and then you will come up with the same relationship that proves that using this will come to this end. Now this derivation will be considered one of the derivation requirement for you during the final. So we will go through that later on for your final test. The final have one question related with derivation. Is using Biot-Savart law to come with this equation about infinite current carrying getting the magnetic field. So please put a notice on that. So now we go back to something more interesting, starting the section on the one we are going to do is on the magnetic force on a current carrying conductor. What we're looking at is when you go through the magnetic field, if there's a current carrying wire, what would happen to the wire? Does the wire move or so forth? In generally, what we try to say is section 22.5, say magnetic field. Magnetic